Record. Okay, great. So good afternoon, everybody. So as you know, tomorrow we have a lab. In this lab, we're going to have a quiz on shift and rotate instruction, Boolean logic instruction, and bit test and manipulation instruction. These three sections. The lab also is on these three sections. So you need to study these three sections to do the lab and also to solve the quiz. Okay. Today, there is one example. I'm gonna explain it here before I start stack. We are very close to finish this chapter. Maybe today or Wednesday. Maybe by Wednesday you can finish this chapter. Anyway, so let's talk about this example. In this example, I give you like here. I'm telling you we have a car here, okay, and the left door has a sensor, and the right door has a sensor. This sensor should tell you if the door is open or closed, okay? And then, so for example, if the door is open, it's gonna put here, so there is a pin here. This pin is connected to a sensor. For sure, you will understand this part more in chapter 3 because we're gonna do it all the time. So if the door is open, so this one is gonna put 5 volt here. If the door is closed, so it's gonna put 0 volt here. And as I told you, this is pin, external pin, okay? And as I told you, this pin is internally connected by the hardware, so that if there is 5 volt here, I'm gonna put 1 here. Automatically, if there is 0 at any time, this one is gonna be changed to 0 volt, okay? So from software point of view, all what you have to do, you have a byte at location 0, okay? And if you want to know if the door is open or closed, you have to check bit number 6 for left door, okay? If you want to know if the right door is open or closed, you have to check bit number 5 here in this one. Is that okay? So you have 2 bits. Every bit of them is going to tell you if one door is open or closed, okay? Also, I told you the cabin, the light of the cabin is connected to bit number 1. That means if I want to turn the light on, all what you have to do, I have to write 1 in this bit. When you write here 1, the hardware is gonna put here 5 volt to turn the light on. If you want to turn the light off, you have to put 0 here in this bit, so that the hardware is gonna put here 0 volt to turn the light off. Okay, so you have two bits. You are gonna read these 2 bits here. Okay, and you have 1 bit you are gonna write to this bit. By the way, for sure I'm gonna explain later all of that. These two pins, we call them input pins. Why? Because the data, they are gonna read these pins all the time. You are gonna read, but this pin, well, we call it output pin. Output pin, as I'm gonna explain later, because all the time you are gonna write. That's why it's called output. Anyway, so now the problem became very simple. I have 1 byte. I need to check 2 bits in order to know if the door is open or closed, and then I have to make a decision to turn the light on and off. And to do that, I'm going to give you several logics. I'm going to give you different logics. I'm going to tell you, as you will see right now. Okay, so let's go to the example here. Yeah, here. Okay. So, for example, this is the first logic. I want to tell you, I want to turn the light on when the 2 doors are open. Okay, I wanna program the car this way. The only way to turn the light on, the 2 doors are open. Okay, I want to do this way. For sure, I know most cars don't do this way. I know in most cars, if 1 door is open, the light is on usually. Okay, but anyway, I want to do this way. So that means if the 2 doors are open, that means there should be 1 and 1 here for open. Okay, 0 for closed. Okay, so that means if I want to translate this sentence to like programming, that means if these 2 bits are 1s, so bit 1 should be 1 to turn the light on, right? That's what I'm going to do right now. So now I'm going to check these 2 bits, bit number 5 and bit number 6 in the location 0. That's what I did. So here I want to check if both of them are 1s. So what I did here, guys, branch if set. So if the 2 bits, and then I put 1 and 1 here. So if these 2 bits are 1s, go to light on. So if bit 5 and bit 6 are 1s, go to light on. So what should I do in the light on? I have to turn the light on. How can you turn the light on? Just to put 1 here. How I can put 1 here? Bit set. I told you this is the easy way. If you want to set some bits or clear some bits, bit set, bit clear. The easy way. Okay. So bit set. So the way I did it here, I said bit set, location number 0, and then I put 1 here in the mask, because this is, I'm telling the instruction, I want to turn this bit on, right? However, if this branch is not taken, that means bit 5 and bit 6 can be any of these cases, 0, 1, 1, 0, or 1, 1, any of these cases, okay? In this case, I have to turn the light off. So that's what I did. I said bit clear, now this one off, turn it off, okay? And then, and this is a common mistake, please don't do it. It's a very naive mistake. It's gonna make a lot of errors. So try to avoid making mistakes to save your time. So, and then I have to skip this one. Because if you forget to write, because I already, because I have to execute this one only if the 2 bits are 1s. Otherwise, I should not execute this one. That's why I need to skip. Once I come here, I have to skip. If you forget this one, you are gonna turn the light on no matter what. So on all cases, you are gonna turn the light on. If you jump here, I'm gonna turn the light on. If the branch is not taken, I go this way, I'm gonna turn the light on anyway. Okay, guys, any questions? Okay, any question? Okay, I'm gonna change the logic now and see how can we do it. So now I'm gonna change the logic. I'm gonna say I want to turn the cabin on if either door is open. So if anyone is open, okay, that means, you know, if I have 2 bits, I have 4 cases: 0, 0, 0, 1, 1, 0, 1, 1. Okay, so 0 means that 2 doors are closed. So based on this logic, if it is 0, 0, that means the light should be off. Any of this case, the light should be on, because I told you if either door, here 1 door is open, here 1 door is open, here the 2 doors are open. Okay, that means when I check these 2 bits, if it is any of these cases, I have to turn the light on. Otherwise, I'm gonna turn the light here on, here off. Okay, but the instruction we have is gonna check if all the bits are 1s, all the bits are 0s, right? So the instruction I have is can catch or can find this case, right? That's what I did here. Look here. I'm gonna say branch if clear. So if the 2 bits are clear, which is this case, please go to light off, as you see. For sure, in light off, I have to turn the light off. How can you return the light off? Put 0 in bit number 1. How I can put 0 in bit number 1? Bit clear. Very easy, right? Otherwise, if the 2 bits, anything else, like any one of these cases, the branch is not going to be taken. That means I'm going to go this way. Okay. Once I come this way, that means I have to turn the light on using bit set this way. Very easy. Again, if you turn the light on, you have to skip. So if this is the case, I have to skip this one, because I should not execute this one and this one in any case, right? Either this one or this one. Okay, guys, any question? Okay. Okay. I think I'm gonna have one more example before I do stack. So for example, I want to do it in a different logic. Okay, I want to turn the cabin light off if both doors are closed. I want to do this way. Okay, so if the two bits are 0, 0, please turn it off. Again, very easy. So the way I did it here, because I'm gonna use branch if clear, because branch if clear is gonna check if the 2 bits are 0s. Yeah, so if the 2 bits are 0s, please come to here. Otherwise, come this way. Okay, so once I come to here, I'm gonna turn the light off, as you see here. Okay, once I come here, okay, I'm gonna skip. I don't want to do anything, so I'm gonna skip. If you want to do anything, you can do, but I don't want, so I'm gonna skip. Okay, guys, is that okay? Let's start a new topic. Okay, any questions? Okay, so the last thing I explained is if you have a byte, how can you check some bits? Okay, how can you check some bits in a byte if they are 1s or 0s? I explained this. We're gonna you do it all the time, as I told you, because here in the board, every switch, as I'm gonna do in chapter 3, every switch is connected to 1 bit, 1 pin, and the pin is connected to a bit, right? So if I want to know if the switch is connected or not, I need to know if this bit is 1 or 0. I don't care about the other bit. Every switch is connected to a bit, right? So this is one thing I explained. The other thing I explained was how can you manipulate some bits and don't change the other bits. So if you have a byte, how can you set one bit or more? How can you clear? How can you set? How can you flip some bits and don't change the other bits? Okay, again, how this can be useful, as I told you. For example, here these LEDs are connected to eight pins, and every pin has a bit internally. So once I put 0 in this bit, the hardware is gonna put 0 volt on the pin. Once I put 1 in the bit, the hardware is gonna put 5 volt on the pin, right? And then I make the hardware so that when I put 5 volt here, this one should turn on. The electronic circuit should turn on. When I put 0 volt, the electronic circuit is gonna turn it off. Okay. Anyway, now I'm gonna move to another topic. This topic is called stack. So first, in the beginning, I want to make a definition. What do you mean by stack? What this means? Then I'm gonna explain how it is useful, how we will use it. Okay. So number one, stack is a part of memory. So I'm gonna take a part of the memory. I'm gonna make it stack. Okay, very clear. So I'm gonna take part of the memory. I'm gonna make it stack. Okay. However, this part of the memory is gonna be reserved for a special purpose. Okay. So that means, before I continue, very simple, what we did right now, guys, is we had a memory. That's what we did so far. Yes, we had a memory. And then we said we are going to have one part for the code, for the program. That's what we did. Also, we said we are going to have one part from 1000. This should be for data. So if you have a variable, if you have array, any data should be in this part of the memory. So I divided the memory into 2 parts. Okay, one for code, one for data. Now I'm gonna divide the memory into 3 parts because also I need one part. So as you will see right now, I'm gonna take one part of the memory. I'm gonna call it stack. Okay, so let me continue. But that's what you should understand. After this topic, now the memory should be divided to 3 parts. Okay, data, stack, and code. Okay. So now you are going to take a part of the memory. That means a stack, just a bunch of bytes. Yes, it's just a bunch of bytes. Memory, it's a memory, but it's going to be used for in a special way. Okay, what you mean? That's what you need to justify, or that's what you need to explain. What you mean by special way? That's what I'm going to explain. I mean here in stack, the way we are going to read or write these bytes, because again, stack is memory, right? Memory means bytes, means you can read or write. You still can read or write. However, the way we are going to read or write is going to be different from what we did before. Okay, I'm going to give you more details. Let me tell you what we did before. The way we read or wrote, or what we did before is, how can you read or write? We can call it random access. So what we did before, it was random access. What do you mean by random access? Random access means there is no a specific order to read location. I can read any location. I can write to any location. There is no specific order, right? So for example, I can read location number 10. After 10, I can read location number 7000, right? This is the way. That's why it's called random access. This is what we did before. Is that okay? I can read any location in the memory randomly. There is no a specific way or a specific order to read memory. Okay. However, stack, still it is a memory, but the way you are going to read or write is different from what we did before. How? Because in the way I'm going to read or write stack is last data in is first data output. So you cannot read, you don't have a freedom to select to read any location. No. Okay, there is a specific order. This is a specific way to read or write. So the last data you write to the stack is actually the first data you are going to get from the stack. Okay, so last data you write to the stack is actually the first data you will get from stack. Okay, I see the difference between random access and this one, but still it's not clear. That's okay. Just wait. You are going to learn more. But what I'm saying right now, you can tell the difference. In case of random, I can read any location. Okay. In case of a stack, you cannot read any location. There is a specific way. Last data in should be the first data output. Last in, first output. Okay. Great. So let me show you a picture. Hopefully this picture you will understand better what I mean by stack. Very good picture. For example, look at this picture, guys. If you have, can you see this stack of plates? Can you see the stack of plates here? Okay. You can imagine every plate like one byte. Okay. That means, so you can imagine this is the stack. So you can see this is like a stack. Okay. You can imagine every plate here is like 1 byte. Is that okay? Let me ask you a question. Now, if I want to write to the stack, where I have write to the stack, it means I want to put a plate on the stack. So if I want to put a plate here, should I put here a plate in the middle? No, we don't do that. So if you want to put a plate, you have to put here in the top of the stack. Is that okay? So if you want to write, you have to write in the top. Okay. If you want to take a plate, if you want to read, take a plate means you want to read. If you want to read, so I have to take the one at the top of the stack, the one at the top of the stack. You got what I'm saying? That means I cannot get randomly anyone here. No, you cannot. So that means that if you need, so that means I should have a location. This location I have to call it top of stack. The top of the stack. Okay. So I should have this location so that if I want to write, I have to write on this location. If you want to read, I have to read from this location. Similar, reading or writing, similar of taking or putting a plate here. Is that okay? Also, you can see how last data in is actually first data output, because the last plate I'm gonna put here is actually the first plate I'm gonna get. Is that okay? Let me explain again, guys. So what I'm saying again, very simple. A stack is a memory, a part of the memory, but the way we're gonna store data or read data or retrieve data from the memory, from stack, it will be different from what we did before. The idea is that's why I have boxes here, because this will be my stack. Okay. So for example, guys, imagine every box here is like 1 byte in the stack. Okay. So for example, this is the stack. So I should know what is the top of the stack, because if I want to write, I have to write on the top, right? So if this is my stack, okay, I want to write this pipe. That means I have to write it here, okay, this way. So this is the last n. This is the last n, right? I want to write more, so I have to write at the top, okay, because the top is, every time I write, the top is going to change. So in the very beginning, this was the top of the stack was here, okay. When I write, actually, I'm going to have a new top, as you will see right now, okay, now, okay. So every time I read or write, I have to write at the top, or I have to read from the top. Now I want to write 1 more byte, so I have to put it here at the top, and now I'm going to have a new top here. Okay. Now I want to read. Okay, so I have to read the one at the top, this byte, and now the top is going to change. So you can imagine that the top of the stack should always point at a certain location. If you want to read, I have to read from this location. If you have to write, you have to write at this location. Is that okay? So you can see, guys, the top of the stack here is like a pointer. Why it is a pointer? Because it should register, it should store address, right? Similar to what we did before in many places in this course. So now the top of the stack should be address. Which address? Address of the top of the stack. Is that, you got what I'm saying? So it's like a pointer. So if you want to read, you have to read from this point, from this location. If you want to write, you have to write at this location. Is that okay? Remember, we used already pointers before in this course in many places, like we used it like PC. PC is a pointer, right? PC is pointing at the instruction you should execute. Also, just in the last lab, we used registers X and Y as pointers. Okay, so now, yes, first of all, let's agree that stack, it's a memory. Memory means I have to, memory means read or write. That's the only thing memory, is the only thing memory can do. I just read data or write data, right? So stack is memory. So stack is just read or write. That's true. However, the way we're going to read or write from stack is going to be completely different from the way we did it before. In stack, what we did before, you can just read from any place, right? You can, that's why what you did before, you have to give me address. I want to read the byte at location 7,000. I want to write at the location 7,000 because randomly you can write anywhere. You can read from anywhere. Is that okay? However, in stack, it's not anywhere. In stack, I have a point. I have this top of the stack. If you want to write, you have to write on the top. If you want to read, you have to read from the top. That's why, as you will see later, if I wanna write to the stack, I'm not gonna tell where. I'm gonna tell the stack write. That's it. I'm not gonna say where. Okay. If I wanna read, so I'm gonna just read, I'm gonna say stack, give me 1 byte. That's it. I'm not gonna say from where, because always we have a certain location here for reading or writing. Okay. So again, you can see, so that's why I need to know, I need to store the top of the stack. I need to know which address is the top of the stack, which address, because, and I need to keep track of this address, because if I want to read, I have to read from this location. If I want to write, I have to write this location. And this should be dynamically changes. Okay, for example, if this is my stack here, guys, so this location, top of the stack is here. If I want to read, so now it should be here. So I'm gonna read this one. So it should be here automatically, right? If I want to write, so it has to be here. If I want to write more, it has to be here. So we have to be here. So I should have a pointer at the top of the stack, and this pointer should be automatically updated every time read or write. Is that okay? So, okay, but which pointer I'm gonna use? Yeah, now there is a special register. I told you in the very beginning, I told you I'm not gonna talk about this register until I come to the stack. This is special register, we call it SP, stack pointer, stack pointer. So this is something like PC. It has a special purpose, but PC should point at an instruction. Stack pointer, it has a special purpose, and it should point at the top of the stack, okay? And automatically updated. So let me continue, and then after that, I'm gonna see if you have question or not. So the way last in, first output, this is data structure. So this is one way to define a stack. So some people like to define a stack as a stack is like variable length array. So it's like variable length. Why it is variable length? Because every time if I write, it's gonna grow. It's gonna be too much. Read, it's gonna shrink. So that's why it's variable length, because every time you write, it's gonna grow. Read, it's gonna shrink. Okay, that's why you call it variable length array. And the way you are gonna read or write from this array is last in, first out. Is that okay? Okay. Now, guys, I'm just now making a definition. Until now, I didn't explain, but that doesn't make sense. Why? I sometimes I need the last data I write should be the first data I get back. Okay? In what situation? In what application? I may need something like that for sure. Otherwise, if I don't need it, they would not make it, right? So for sure, as I'm going to explain later. So now don't worry, try to now focus on the definition, try to understand what I mean by stack, how it works, how can we use it, and for sure later I'm going to explain how it can be useful. Okay? So in some cases, as you will see right now, in some cases, I need something like that. I need the last data I write is the first data I get back. Okay, I'm going to explain it later, but now let's continue on the definition. So for example, guys, here I give you example here. Assume this is the stack. This is stack. So the stack is storing 1, 2, 3, 4 bytes, as you see here, 4 bytes. And now 1005, this should be stored in a stack pointer. So this is the top of the stack. Now I want to read from the stack. As I told you, I'm not going to tell which memory location I want to read. That's why this is the main difference between reading or writing from stack and reading or writing from memory, from the normal memory, okay, or what we did before. So I'm gonna say the stack I wanna read, okay? So when I say I wanna read, you don't have option. So I'm gonna give you the one at the top here. So I'm gonna give you this out, and now stack pointer is gonna be updated. So now this is the stack pointer. It's gonna shrink automatically. So now the stack had 4, now it has 3, right? Now, what if I want to read more? I'm going to say stack, please stack, I want to read, okay? So the stack is going to give me the one here, and again, stack pointer is going to move to here automatically, okay? Stack pointer is here. Now, I want to tell the stack, I want to write, stack, please take this information, store this information, or store this pipe. So the stack is going to take this one, put it in the top here as you see. And also stack pointer is updated as you see here. Okay, guys? Okay. But let's agree on something, guys. From now on, I'm not gonna use, usually we don't use, yes, we read or write, but we don't use the word read or write with a stack. With a stack, we don't use read and write. Yes, it is read and write, but we use different terms. We use here, this one, we call it, when you read, we call it pull, you pull. When you write, you actually push. So, okay, guys? So here with the stack, instead of using read or write, it's the same thing. You still read and write, but we don't use read and write. We say pull and push. So if you want to read from the stack, you pull. If you want to write to the stack, you push to the stack. Any question? Okay. Now, I told you guys, now we're gonna divide the memory into 3 places. The memory will be divided 3 places. Yes. So as we did before, we're gonna start, our data is gonna start from 1000. Is that okay? From 1000. Our code, our program will be started from 4000. However, our stack should go this way, grow this way. Our stack is gonna be this way and to grow this way. Okay, that means how I can do that? How I can tell the stack should start from here, or the stack should start from here. Okay, in the very beginning of your program, you have to initialize the stack pointer. In the very beginning of your program, you have to initialize the stack pointer. That means in the very beginning of your program, we have to, if it is not already there, you have to write something like load. So in the very beginning of your program, you have to write something load stack pointer, okay? And then you have to say 4000 $sign here to initialize. This is the beginning. Is that okay? So now the stack is empty. So here in the very beginning, I put the stack pointer is here. Okay. And there is one point here, guys. Maybe you didn't observe in the previous example. Let me go through it again. Here. In this example, guys, you can see the stack, the way I made the stack here, the stack is gonna shrink. When it shrinks, it's gonna shrink from the small address to bigger addresses. When it grows, it's gonna grow to the lower addresses. You can see right now. So for example, now the stack pointer here, the stack pointer is 1007. So the way I'm gonna design our stack is gonna grow this way in smaller addresses, as you see here. Is that okay? So I'm gonna start from a certain address, and then if every time you write, I'm gonna go toward this lower addresses, smaller addresses. Is that okay? By the way, this is a design. So maybe this is what we do in our microcontroller here. Okay, we start from a certain address, and then the stack is gonna grow in smaller addresses. Maybe other microcontroller is gonna design it the other way. No problem. It's still the same concept. It's still the same concept, the same idea. Okay, so maybe when you study another microcontroller, you see they are gonna grow from small addresses to bigger addresses. Okay, but anyway, so that's what we do here. That is why, look here, guys. That's why from now on, the way I'm gonna do it is here. I'm gonna say load stack pointer 4,000 $sign for sure. So stack pointer this is the initial value. I'm gonna put it here so that every time you write, I'm gonna grow this way. From big address to smaller addresses, the stack is gonna grow this way. Okay. So let me now. This is a new picture for our. This is a new picture for our memory. So just a simple modification on what we did before. For your data, still you are gonna start from 1,000, and then you are gonna grow this way. Every time you create array, every time you make a variable, it's gonna grow this way. Okay. From 4,000. Okay. So your program is gonna go this way, and your stack is gonna grow this way. Okay. So there are several things here. Listen to me. Look here, guys. Here, this is, we don't have operating system. There is no Windows. Is that okay? This is a very simple computer. Who should do management to the memory? You, programmer. You are the one who are doing management. Is that okay? To the memory. That means, is that possible that, or maybe there is overlap between stack and data, or between code and whatever? Yes, there may be overlap. And this will make a trouble for sure in your program. The program is gonna crash. So you have to make sure when in your program, because now we have three things. We have code, we have data, we have stack. It's your responsibility to make sure they are in separate areas. For example, if I write here too much data, and then in the stack, I write. Yes, this is hardware. The hardware doesn't understand. The hardware is gonna do whatever you tell the hardware to do. That means when the stack, there is overlap. So when I write, you are gonna overwrite your variable, your arrays. So for sure, this is gonna make a mess. This is gonna make like your program is gonna crash. So you have to make sure, guys, you have the space free from 1,000. You have to make sure if you have this amount of data, you have to make your stack cannot. It shouldn't cross this border, right? It's just your responsibility to make sure of that. However, the good thing is for our programs, we're not gonna make so you should not worry about this. I'm teaching. You should not worry. Why? Because we already have enough spaces. I don't imagine that in any program we will do, you are gonna write too much data. I don't think we are gonna need all these spaces, right? However, if you have to make sure for sure they are separate, otherwise there will be overlap, and then you are gonna have a trouble in your program. Any question? Is that clear? The other thing I want to teach you guys is why you selected this number. So why 1,000 and 4,000? How you came up with this number? Can I use the different numbers? For sure you can. For sure you can use different numbers. Okay. However, the reason I selected this number is because in our microcontroller here we have flash memory, and this flash memory starts from 4,000. So I want to use the flash memory for the program, for the code, right? And we have a RAM. This RAM is from 1,000 to 4,000. So I want to use the RAM here for data and for stack. Okay. I want to tell you something. Also, another thing is the way we read or write flash memory is different from the way you read or write RAM, right? It has a different way. I think there is a chapter one. I think the last chapter or at the end of the textbook, there is one chapter. How can you read flash memory? I guess. But anyway, I'm not going to teach this here. But the way you can read or write RAM, as we did, you can just read a byte, you can write a byte, but the way you read or write flash memory is different, right? So I can read a byte and write a byte. Okay, you can write a block of data. That's why maybe you didn't notice it yet, because until now we are working on simulation. But my plan, starting from next lab, I will give you the board, because the next lab is the last lab you can use simulation. After that, you have to use the board. So starting from the next lab, I'm going to give you the board. You have to make sure the board is connected to your computer. So please try to read chapter lab 1. In lab 1, I give you some instruction how you make sure the board is connected to the the computer, your laptop, so that so when you will see, if you don't use simulation and you use the board, you will see in the very beginning when you write your program, it's gonna writing to flash memory. But anyway, so what I'm saying, guys, is that I cannot put my data here because I can read for sure. You can read any byte here, but you cannot write. So you're gonna have some trouble to write because the way you write to flash memory is different from stack. Anyway, so what I want to tell you guys is that why I selected 1,000 and 4,000 here, guys. Okay, I'm gonna tell you why. In the very beginning, when I started to teach this course, I didn't ask a student to use 1,000 and 4,000. I give them the freedom to do whatever you want to do. Okay, so that means you can, for example, start your data from 1,000, and then you can start your code from 7,000, and then you can start your stack from whatever. So I just leave it to the student, decide whatever you want to decide. Okay, but I turn it out. This makes some trouble. Why? Because overwriting. Okay, so what happened before? You didn't make good management to the memory. So for example, you can, when you write, if I put my code here, and my data here, if you continue writing, you are gonna overwrite your code, right? Same thing for stack. You are gonna go back. So I found the best way is I try to give you the maximum space for data, for stack, for code. Okay, guys. So I just want to tell you, it's this because this is a very low level programming. You have the complete control. You have the complete freedom to select whatever you want to do. Okay. So here, but again, the reason I selected 1,000 and 4,000 is just because if you start from here and the stack is gonna grow this way, you're gonna have the maximum space. But you have to be careful here. You should not. You have to make sure there is no overlap between here and here. Is that okay? Any questions? Okay. So now I'm going to explain how can you write a byte to stack. Okay, the idea is very simple. I'm going to explain the idea first before I choose the slide. So, okay, I wanna write a byte to the stack. Look, guys, stack pointer is here, stack pointer is here, right? So what happens? Stack pointer should be decremented by 1. This number 1 to point to a new location, because I told you if I go this way, you decrement. You go this way, you increment. This is the way I designed this stack. So stack pointer here. I want to write a byte. So number 1, decrement stack pointer. Number 2, write the byte at the location pointed by the stack pointer. Okay. So that's exactly what I'm explaining here. Look here, guys. Write a byte to stack. That's what I'm gonna call it push. So I'm not gonna use the word write again. With stack, we use push. So I want to push a byte. So when you push a byte, actually 2 things should happen. Number 1 is stack pointer should be decremented by 1, because when you decrement, the stack grow. Okay. So here, for example, if I'm here, if the stack pointer is originally at 1,005, so now it should be at 1,004, as you see here. It's number 1. Number 2, write a byte to the location or at the location pointed by the stack pointer. Is that okay? This is how can we push to the stack. Now I'm gonna teach how can you pull or how can you read from stack. It's the same thing. Look here, guys. Stack pointer is here, so I want to read a byte. So I'm gonna read a byte pointed by the stack pointer, right? That's enough? No, you have to update the stack pointer. So you have to increment the stack pointer by 1, right? That's exactly what I did here. So if you see here, guys, this is the stack. This is the stack is this way. Stack pointer is pointing at 1,005. So I wanna pull a byte. I wanna read the byte. So number 1, I'm gonna read the byte at the location pointed by stack pointer. This is number 1. Number 2, I'm gonna increment the stack pointer by 1. Is that okay? Guys, you don't need to do these 2 things together. You don't. We have one instruction. This instruction is gonna do both of them. So I'm gonna teach right now. We have pull instruction. This pull instruction is gonna do these 2 things. It's gonna read and update the stack pointer. We have push instruction. This push instruction is gonna do 2 things, right? It's gonna update the stack pointer and is gonna write. Okay. I'm explaining, so you don't need to do, you don't need to increment or decrement the stack pointer. This is done automatically by this instruction. I'm explaining how this instruction works. Okay, guys, any questions? Okay, let me tell you something just easy by common sense. I explained right now how can you read or write a byte. Can I read or write a word? Yes, you can, similar to what we did before. Almost all the instruction I took before, most of the instruction I took before can be, some of them for bytes, some of them for word. The same thing here. We have push instruction for bytes. We have also pull instruction for bytes, and we have push and pull instruction for words. How it would be different if it is for words? How it would be different? Very easy, different. How it would be different? Very easy. Number one, a stack pointer is going to be incremented by 2 or decremented by 2, right? Decremented by 2, incremented by 2. This is one difference, right? Instead of 1, it should be 2 because 2 location. Number 2, instead of writing 1 byte, I'm going to write 2. So let me tell you, for example, here. Stack pointer is here. Stack pointer here. I want to pull a word, so I'm gonna take this one. I'm gonna take this one, okay, and then I'm gonna increment the stack pointer by 2. Makes sense, right? Now, what if I want to write 2? So what happens is that I'm gonna decrement to 2, then I'm gonna write a word. Is that okay? So it's almost the same thing. The only difference here, you are going to add 2 or subtract 2. You are going to put 1 byte or 2 bytes because it's going to be 2 locations. Anyway, so here I want to teach the instructions we have for push and pull. So for push instruction, we have push A. So this one is going to store the value of A at the top of the stack. Okay, you are going to store register A, the value of register A. This one, push B. So you are going to store the value of register B to the stack. Okay, these 3 instructions push for a byte. We have push C, CCR, right? We have push D, we have push X, push Y for words, right? That's all what we have. We have for pull, we have pull A, pull B, pull C. See here, guys, CCR, the flag register, okay? Because we don't have C flag, but we have CCR flag, which, sorry, we don't have C register, but we have CCR register, which is a flag register. Okay, anyway, we have pull D, pull X, pull Y. Okay, so what this means? It means I want to store the value of A in the stack at the top of the stack. This instruction is not going to change A. So if register A is storing 3A, after you execute this instruction, still register A is storing 3A. What happened? I just store this value at the stack. I put it in the top of the stack. Same thing for this one, same thing for this one, same thing here. Okay. What about pull? What pull is going to do? Pull is going to do what is going to do. This is a stack. I'm going to read a byte from the stack. I'm going to put it in register A. So this instruction is going to change register A. You're going to overwrite register A. So this one, I want to read a byte from stack, put it in A. Here, I want to read a byte, put it in P. Sorry, B. Put it in C. Put it in G. Here, I'm going to read the word from stack, put it in G or X or Y. Is that okay, guys? Okay, so here I'm just want to give you examples about these instructions before I talk about how stack is useful. Okay, how you can use it. So, for example, if I say that's exactly what I explained right now. So when I say push A and the register A is storing 3A, so what's going to happen is 3A is going to be written on the top of the stack, and the top of the stack is going to be updated as you see here. Okay, because this is the last in. If you want to take from the stack, this will be the first output, last in, first output. Is that okay? So here, pull E. Pull E means I want to read the top of the stack, the byte at the top of the stack. I want to put it in A. So if this is the stack, before you execute this instruction, after you execute this instruction, so the top of the stack, which is FF, is going to be stored in A. And now the stack pointer should be at 1006. It was at 1005. So when it shrinks, you add. When it grows, you subtract. Okay. Any questions? Okay. So before I continue, guys, let me summarize what I said. And if you have any question, let me know. So what I'm saying now, I just explained what I mean by stack. I told you stack is just a part of the memory, right? but we already used the memory before. We already used load, store, move. We already used the memory before. But stack is different. The way you are going to read or write is going to be different. I'm not going to tell unlike what we did before. I'm not going to tell which location you have to read or write. I'm not going to say that. Okay. So what's going to happen is I'm going to just tell the stack, give me a byte, store a byte, give me a byte, store a byte, give me a word, store a word. That's it. I'm not going to say where. Why? Because there is a specific way to read or write from a stack. There is a certain point, which is the top of the stack. And the way I want to design the stack is, it's a memory. Yes, it's a memory. However, the way I want to use the memory is last data in, first output. Until now, I didn't explain in what application I need last in, first output. You got what I'm saying? So anyway, so I'm going to explain this one, but this is the way we read or write. And how can we implement? Again, I need to make a memory. This memory, the way this memory retrieve or store data is last in, first output. That's what I want to do, right? How I can implement this idea? I'm going to implement it using a pointer. I should use a pointer, which is a stack pointer. So the stack pointer should help me to implement the stack. Is that okay? So stack pointer is here. If you want to read, you have to read from here. If you want to write, you have to write on this one at this point. Okay. That's why stack pointer has always, it has to point at the top of the stack. Okay. All what you have to do, guys, in the very beginning, in the very, very beginning of your program, you have to initialize the stack pointer. And that's it. So you can initialize the stack pointer by 4,000. Is that okay? In the very beginning of your program. And then you read, write, and then automatically stack pointer is going to be updated when you pull or push. Okay? You just initialize it in the very beginning. Okay? Any questions? I know what you are gonna let me guess, but I think you wanna ask me why I'm not sure. I'm just making a miss, maybe I guess. So maybe you wanna ask, because I was about to talk about this one. Why I initialize the stack point by 4,000? Because at 4,000 we have an instruction here. You got what I'm saying? So how I put the stack pointer here, and also we have an instruction here. Very simple. Because when I write, I'm going to decrement it by 1. So actually, so your first location actually in the stack is not 4,000. Your first location actually is 3FFF. Remember, I know some of you make these simple mistakes. The byte, the address before 4,000 is not 399. 3,999. No, this is at Walmart. Okay, when you go to Walmart, it's going to be 399. Okay, this is a decimal. That's what we are using, right? But in computers, the number before 4,000, because it is a hexadecimal, should be 3FFF. Is that okay? Anyway, so when I say the beginning of the stack is 4,000, right? That means actually the real beginning should be 3FFF, which is true. Why? Because if stack pointer is here, I want to write. You decrement and write. Decrement, you write. You get what I'm saying? So when I point at 4,000, actually, that doesn't mean I'm going to start from 4,000. You decrement and write. Is that okay? So your actual beginning is this one. Because by common sense, I cannot use the same location for two different things, for code and for stack, right? This was your question.
Yes.
I won, right? Okay. You have any other questions? Okay, great. Okay, guys, clear, guys? You have another question? Yeah. Yes.
Okay.
Yes, you don't push. I'm explaining how push instruction is going to work. So all what you have to do, you just say push or pull. I'm explaining how this instruction is going to work. So the way this instruction, do you remember when I say, for example, before branch if clear, I told you this instruction actually is going to do three operations. Okay, in one instruction. This is the same thing. So this one is going to decrement or increment stack pointer. Also, is going to write. Okay, so you don't need to worry about the stack pointer. You just, once you initialize the stack pointer at the very beginning of your program, just leave it. Okay. Any questions? Okay. Someone should ask me somehow very simple question. Okay? So you told me you should initialize the stack pointer here at 4,000, and you told me When I initialize at 4,000, actually, I'm going to start at 3FFF. Yes, that's true. Okay. So someone can ask me, can I pull in the very beginning? Can I pull? Okay. First, you can. Yes, you can. However, that doesn't make sense. You answer what I'm saying? In the very beginning, the stack is empty. In the very beginning, the stack is empty. Okay. So if you pull, yes, you are going to get something if you pull. Okay. However, that doesn't make sense, right? So yes, hardware may allow you to do that. However, if you are still in the very beginning, you didn't push, you didn't write yet, you should not pull before you write, by common sense, right? So if you do it, you will get something, but that doesn't make sense, right? It doesn't make sense to do that, right? Similar, for example, if you say integer I in C language, and they, for example, you will k equal to I plus 7. But I is uninitialized. You didn't initialize it. Can I read it and add something to the value there before I put some value there? Doesn't make sense. You have to first to put some value. Same thing again. So in the very beginning, guys, as long as the stack, or maybe we're gonna have the same problem. Look here, guys. For example, I'm gonna push 100 bytes. Then I'm gonna pull 200 bytes. Does that make sense? No, it doesn't make sense, right? Because once you pull 100 bytes, the stack should be empty, right? The problem is the hardware is not going to give you error, but this is something you should consider. You should consider that if you push 100, you have to pull no more than 100, right? But the hardware is maybe it's not going to give you error, right? But it doesn't make sense. Okay. Anyway, any question now, guys? So that's what I said. I explained how it works. I explained the instruction we have, different instructions here. I give you a couple of examples. Now, this is the most important thing. Okay, it looks interesting, but how can we use it or how it is useful? Because the idea of last in first output, it looks like weird. Last in first output looks weird. Okay, I'm going to tell you why they made the stack, how it is useful. Make sure every computer system is using stack. That's for sure. So I'm sure your smartphone is using stack. I'm sure your laptop is using stack. Okay, you will understand why now. Okay, but anyway, but for sure it should be used. First thing here, look here, guys. Do you remember just last lab? In the last lab, you remember what is the pin? Yeah, in the last lab we had while loop, right? And then I used register X to point on one array. I used register Y to point in another array. Okay, and then so X should store some value. I should not destroy X because I need this value. I should not destroy Y because I need it. Okay, so I don't want to lose the value of Y. However, here, as you remember, we tried to do multiplication. However, the multiplication is going to store the result in Y, or you have to put something in Y. So the multiplication instruction here is going to destroy your pointer. So the way we did it in last lab, I told you, you have to store it in some memory location. For example, you can say here, store Y at location 7,000. Is that okay? And then here you say, load Y at 7,000. So because I need this value, I need the value at register Y. If this is register Y, I need the value there, but still I need register Y to do multiplication. So what I did, I'm going to keep this value in a memory location. I use Y, and then I'm going to get it back. So that's what we did. Okay. Okay, I have a much better idea to do that. Okay, what's wrong with that? So what's wrong with this idea? I'm going to tell you what's wrong with this one. It can work, but it has a lot of problems. The problems is you need to memorize what memory location. You need to memorize what memory location. It may be easy if we talk about only one register. What if you have like 10, 20 register, 10, 20 values I want to store, and then I want to get them back? What can you do? Anyway, so much better way, because you don't need to memorize. You don't need even to reserve memory location or even memorize them. So a much better way to solve this problem is by using a stack. You don't need to worry about memory location. So instead of doing what we did here in the last lab, you can simply say push Y, and then I'm going to say here pull y. That's it. I don't need to reserve a memory location. I don't need to worry about 7,000, 8,000. I don't need to worry about anything. Put in the stack, give it back to me. That's it. You got what I'm saying? So even if you have many values, as we'll do later. For example, I'm going to say push A, push B, push X. You can push too many things, and then you can pull them back. Easy, very easy. Okay. However, as I'm going to explain later, the way you push should be opposite of the way you pull. Otherwise, you are going to make a mess. It's not clear. Okay. So because last in is the first output. So if the last one you push is Y, so the first one you pull should be Y as well to get the same value. Anyway, I'm gonna explain it later. Don't worry about this one. So anyway, so I give you here another example. How can you use a stack? How a stack can be useful for you guys in this example. For example, I want to make a loop. And I want to use register A here in this loop. I want to use register A as a counter for the loop. Okay. So I'm gonna start from 10, and this is my loop. Decrement. You remember this example as well. Decrement and branch. So here the loop counter is register A. So register A should, in the first iteration, register A should be 10, and then 9, and then 8, and so on, because it's a counter, right? However, what if I want to use here in the body of this loop, I want to use register A in multiplication, in division, anything else, I want to use register A. Same idea. You have to store register A somewhere, because this is a counter. I need this value, and then you can use register A, and then you have to return it back. Okay. Again, the very easy way to do that, just push and pull. That's it. Okay, guys, this is a very easy way to do. Another interesting thing here we can do with stack. Look here, guys. If I say push A, push B, right? And then I say pull A, pull B. You know what I did? You shouldn't read this one. So I push A, push B, right? So the value of A, and then I put the value of B, right? Push A and push B. And then when I get back, I'm going to get the value of B back. But I'm going to put it in A. And the value of A, I'm going to put it in B. So if you do this way, you are going to do swap. So if you use the same order, you actually, so here, what you mean by order? A and B. A and B. If you use the same order, you actually is going to do swap, right? However, if you use opposite, so if I pull this way, I'm going to pull this way, so B and A, right? So here it's going to be no change, right? Because the last one is B. When I take it, I'm going to put it in B, and then next one is A. I'm going to take it in A. Okay. So this is also, you can use it this way. Another thing we're going to do all the time is, look at this one here, guys. If I say something like that, look here, push A, push B, push X, push Y. Is that okay? So I just want to store their values in the stack, right? And then I can change A, change B, change X, change Y. And now, if I want to return the original values, you can take them from stack. However, it's going to be the opposite order. So here the last one was Y, so the first one is Y. Next one was X, so next one here X, B and A. Just because last in first out. Is that okay, guys? So if I want to use the registers, but I want to store the original values somewhere, you can push all of them in the stack, and then you change them, and then get them from the stack back. So you are gonna take the original values back. Is that okay, guys? Any questions? By the way, we are gonna do this part all the time in subroutines. You know what I mean by subroutine or function? Okay, so I'm gonna explain later subroutine, but let me tell you what is the idea here. Look here, guys. You know, if you have a function or you have subroutines, the idea is that this is the main program. You can call a subroutine. So once I come here, you call a subroutine, and then you come back, right? So you should be familiar with subroutines, okay? So the idea of push-pull, we're going to use it all the time here. I'm going to tell you why. Look here, look, very interesting, look here. Before I call the subroutine, register X, register B, register A, B, X, Y, should have some values. And after I call the subroutines, I need the same values back. For example, X is a pointer. So after I call the subroutine, X should store the same value, right? I don't want to, when I go to the subroutine, it's going to destroy everything, right? So how can we do that? How? Because inside the subroutine, you may need to use A, B, X, Y. You got what I'm saying, guys? So in the main program, I'm storing some value in A, some value in B, X pointer, Y is pointer. So all what I want you to do is, when I call the subroutine, I'm gonna get the same value spec for A, for B, for X, for Y, because I'm gonna use them later in the program. So I'm gonna use it in the program, right? So, but the subroutine itself, it needs to use A, B, X, Y. Okay. So that is why you will see in the next section. Next section is about subroutines, and this is the last section about subroutines. Okay. That's why you will see in this course all the time in subroutines we do something like that. In this subroutine, I'm going to use register A and register X. So I'm going to push A and X, and then I'm going to pull X and A all the time. Okay, so that the subroutine does not interfere. It does not interfere with the main program. So inside the subroutine, I still can use the register without making trouble, without making problem to the main program. You got what I'm saying? So all the time we will do that. If you have a subroutine, guys, inside the subroutine, all the registers you want to use, just use them. That's totally fine. But you have to push in the very beginning, and in the very end, you have to pull them back. Okay, and that's what I did here. For example, here I'm gonna change. I'm saying the register you are gonna change. If I don't want to change this register, okay, you don't need to do that. So here, because in this subroutine, for example, I'm gonna change the register A and X. So I'm gonna push them, then I'm gonna use A and X, and then I'm gonna get the initial values back, so that I don't destroy the values you need in the main program. So that when I go back to the main program, the values of A and B, X, Y will be the same. Is that, guys? Okay, guys? Because keep in mind, we have hardware with only one A. A is a hardware, register is hardware, right? This A is accessible by the main program, is accessible by all the subroutines. So if I modify A in one subroutine, it's going to be modified everywhere because it's only one A, right? This A is accessible by everybody. It's one subroutine, it changes A, it's going to be changed for everybody, right? Yes, what's your question? That's a good question, very good question. First, we don't have instruction to push memory location. We don't have, as you see, we don't have instruction to do that. However, that doesn't mean you cannot do it, right? So for example, if I want to push, for example, you have a variable, we call it I. For example, I want to push I. So number one, you have to load A with I, and then you can push A. You know what I'm saying? Yes, you can do that. Other thing, guys, you can also use stack 4. Okay, I can use stack to do something like that. Look here, guys. For example, if I have a string or I have array, whatever it is, I want to reverse this string. For example, I have hello. So for example, I have hello string this way, and I wanna display it in the opposite order. Okay, so this is the array is HELLO, but I wanna display it in the opposite order. So the way I can do it, look here, guys. I'm gonna say push H, push E, push L, push O. Okay, and now because the stack last in first output, when I pull them, I'm gonna pull them in the reverse order. So I'm gonna get O first and then L, E, H. Again, just one idea. You may not need it, but again, this is also one idea to use the stack. Okay, guys, any questions? Okay. The most important, all what I mentioned is not a big deal about the use of stack. Even also, the use of stack is very attractive. In this case, as I explained before, if you want to store, but still I can use memory location. Yes, it's not convenient. It's not very professional to use memory location because I need to remember which memory location. Yes, this idea is great, but still you can do it somehow using memory location. So, but again, push and pull is okay. Actually, to be the most important thing, or the main reason they invented stack is because to implement subroutines. Okay, so if you don't have a stack, we cannot make subroutines. Why? Just I'm not going to explain it now. When I come to subroutine, I'm going to explain to you why. Okay, but for now, you should keep in mind, without stacks, we cannot make subroutines. Okay, stacks. This is the main reason they invented stack. They invented stack. The main reason for that is because to implement, to make subroutines, I need a stack. Okay, but I'm not going to explain it later. I'm going to explain it how stack is essential. How stacks are essential to make subroutines. Okay, I'm going to explain it later. Now, I think I have just examples now. Let's look at these examples. Okay. So, for example, look here, guys. Load stack pointer 1006, as you see here. Okay, guys. So now the stack, this is initialization to the stack. So the stack is empty. If nothing in the stack yet, I'm just initializing the stack. So stack pointer is here at 1006. I told you when I say stack pointer at 1006, so actually it doesn't start at 1006. Actually, it's gonna start at 1005 because when I write, I decrement first and write. Okay. So that means if your stack starts from 1005, you have to initialize with number 6. You got what I'm saying? So if I tell you your stack should start from 1005, so actually I have to put 1006 because if I start from if you start from 1005, by the way, you are not going to write at 1000. You have one byte you don't use because I'm not going to write at 1005. When you push, you decrement and write. So I'm going to start from 1004. Anyway, so here in this example, I started the stack pointer at 1006, right? So now look here, guys, what I did. Okay. Load register A with 20. So here I'm going to store 20 in register A. Okay, and then I'm going to say push A. So when I do that, so now stack pointer should be at 1005, and then I put 20 here. Now, if the stack was empty, now the stack has 1 byte, as you see here, right? Let's see this one. I'm going to say load register B 28. So I'm going to put 28 in B, and then I'm going to say push B. So now the stack pointer, it was at 1005. Now it should be at 1004, and then 28 is here. So 28 is here and 20 is here. 20 is the old value here. Okay. And then here, load X with FF3A, right? Put it and then push X. So what's going to happen? Look, this is the stack right now. So stack pointer should be decremented by 2 now because I'm going to push a word, as you see here. So I decremented by 2, as you see here, guys, and then I'm going to put 2 values. What about the order? The order here is similar to what we did before. The most significant byte should be at the lower location, as we did before. Okay. So this is now the stack is growing. So every time I say push, growing. When I say bull, so it's shrinking. Okay. Before I continue, I have there is a question in the assignment, not this assignment, next assignment. There is a question. I'm telling you in this question, how much space I have to reserve for the stack. Okay, so I give you a program, and I'm telling you how much space the stack will need. Okay, guys. So look here, it's a little bit tricky, but think about it. Look here. the point is that when I push, it grows. When I shrink, it's gonna shrink. Sorry, when I pull, it shrinks. So all the time you see the stack grow, shrink, grow, shrink, grow, shrink, grow, shrink. Is that right? So how much space I have to store in the stack? I have to reserve for the stack. You have to see at a certain point what was the maximum data in this stack. You got what I'm saying? Maybe I'm gonna push 1,000 bytes. I'm gonna pull 1,000 bytes, but I need only 1 byte in the stack. Why? Because push, pull, push, pull, push, pull, right? So I need only 1 byte. You understand what I'm saying? Little bit tricky, but think about it, right? So it doesn't matter. So the size of the stack, it does not depend on how much time you push, because I may pull, push, pull, push, pull. You got what I'm saying? So, but it depends how much at a certain point, how much data was in the stack. So the way you should answer this question, for example, here you push, the stack was 1. At this time, or at this instruction, the stack was 2. Now I push again, so the stack is 3. Then I pull, so the stack is 2. So look how the stack is gonna, the size of the stack over the time, and you have to select the biggest one here. Okay. So now for my stack, I don't need more than 3 bytes, because the maximum data that was in the stack at a certain point, what was 3 bytes. Okay, guys. And again, we are gonna start our data from 1,000. We are gonna start our stack from 4,000. I'm telling you, this is hardware. The hardware does not understand. If you start from here and you say push, the hardware is gonna write. So maybe you are gonna go to your variables, your arrays. You are gonna write some data there. Okay. So for sure, this is gonna, your program will crash. Okay, if you do that. So you have to make sure. And again, I don't think this is something you should worry about. You should understand, but I don't think you should worry too much about it, because my guess for most of our programs, I don't think we're gonna need all this space. This is too much space, by the way. This is not 3,000. From 4,000 to 1,000, it's not 3,000. It's much more, because this is hexadecimal, right? So I think we should have enough spaces here for data and for stack. Okay, guys. Any question about stacks? Okay. So again, let me summarize what I said. Okay, just few sentences. Okay, guys. Number 1, from now on, you should understand that the memory now is divided to 3 places, right? Code, data, stack. This number 1. Okay. Number 2, from now on, at the very beginning of your program, you should initialize your stack pointer to 4,000. It's already there, by the way. You remember when you have like initial program, and I tell you to remove this one and put something else. And so if you look at the instructions written there, you will find one of the instruction load stack pointer was 4,000. So it's already there. Okay. Anyway, number 3, stack pointers are very important to implement subroutines. Is that okay? So without stack, we cannot make subroutines. Why? I'm going to explain in this section, so don't worry about it. Okay. What you need to worry about is how can you use stack? How can you use stack? As I told you before, I give you several examples. As I told you before, I want to use the register X, but I need this value back. Okay. So I'm going to push it in the stack. I'm going to use register X, register A, Y, whatever, and then I'm going to get it back. That's it. Push and then pull. That's the easy way to use it. Okay. Now, rough 1 minute, so I can say something here. Now, guys, we have here in assembly, similar to any programming language, we have something we call it subroutine. And sometimes we call it function. Sometimes we call it routine. I think in MATLAB they call it method, I guess, or Java. I don't remember. But anyway, these are just different names for the same thing. Most of the time, I'm gonna say I myself. I usually use the word function, routine, or subroutine. So they are the same thing. So if I say routine or subroutine or function, they are the same thing. Okay. So what this means? Okay. So okay, I can do it next time. Okay, guys, thanks. Okay, so we are gonna continue it next time. It's 5:15. So this will be the end. This is the last section in this chapter. We're gonna after that we're gonna start chapter 3. Okay. Please, if you have guys, in the coming lab, I want to use the board instead of using simulation. So if you have a Mac operating system, so you need to download, I think, like dual. I already explained what you have to do in lab 1. Okay, you need to download, I think, virtual Windows, something like that, to be able to connect the board. Also, I want you to read how you connect the board in lab 1. In lab 1, I'm explaining how you connect the board. Okay, in the coming lab, we will try to use the board, because starting from lab number 7, we can only use the board. We're not going to use simulation anymore. Okay? Yeah, sure.
So for the lab, then.
Okay, just let me, I'm gonna just